Hi there. Today we're going to look into this paper, End-to-End Video Object Detection with Spatial-Temporal Transformers by Lu He, Qiangyu Zhao, and Xiangtai Li. They propose a transformer-based video object detector which basically consumes multiple frames in the past or, if necessarily, from the future to then detect objects in the current frame. Which problem do we try to solve with this paper? So normally in video object detection, you have something like that you have multiple images of your current video. So you have a scene. For example, you have like frame 1, frame 2, frame 3, and frame 4. And maybe you have in there a little turtle which is moving in there. So you have like, here's a little turtle and it's moving into this direction from there to there. And in single object detection, a detector would go into this image and would detect like a bounding box around this turtle and also say like, okay, this is a turtle. So what you get is like a class, and a bounding box. So like x1, y1 in the image and x2 and y2 in the image. But sometimes the issue is that in these single frames, things are sometimes hard to detect what these things actually are, even for humans. And the idea is to make use of multiple frames. So suppose we had like, this is time step t, and then this is time step t minus 1, this is t minus 2, and t minus 3. It would definitely help us to make use of all these information from all these frames to tell then at time step t, okay, this is a turtle and I know its coordinates x, y, and so on. And in this paper, they do that. So they put all these frames together into one detector and regress then the object class for that time step t and also the regression part, so x1, y1, and so on. And the interesting thing about this whole idea is that they made it end-to-end learnable and also and make use of transformers, and they beat state-of-the-art video object detection benchmarks by a large margin of 3 to 4% more in mean average precision. So let's have a short look into the course overview of this architecture. So what you can see here are so-called reference frames at different time step, like t minus 4, t minus 2, time step t, which is the current frame, t plus 2. So even frames from the future can be consumed to do what? So suppose we had here again our example with that turtle. So we have a turtle here, it's moving, and maybe it's even hiding under something like, or it's partially occluded by another object. And the turtle here is somewhere beneath it. And the detector has issues to detect this in a single frame detector. But with the use of the information of these other frames, it maybe can then infer what that object is and where it is, just by also having more information from the other frames. Okay, so what will be done with these frames. They all get consumed by this spatial transformer. So they all share weights. That means we have trained this one for all these different time steps. And what they produce is some kind of features. So they produce features which are here called something like a feature memory. But also they create object proposals, but they are called object queries here. And we produce them for each time step, for time step t-4, -2, the current time step, and even for future time steps. And the temporal transformer now has a temporal attention mechanism to make use of these features and potential objects in each of these frames. The temporal transformer then creates feature vectors, which are then consumed by a feed-forward network to then create classes and bounding boxes. So this is the overview here. And today we're going to look into detail or more in depth what's happening in here in this spatial transformer, and also how this temporal transformer work and how we can interpret these object queries and feature memories. So to get a deeper understanding of the architecture, we look now into this figure 2. So on the left side we have frames of a certain scene. So we have here multiple frames at different time steps and a current frame. Then we have the whole detector here. And the output results demonstrated there. So on the left side we see a quite funny example actually, because we have here a cat at home which is staring on a squirrel in the garden. And this is somewhat a moving situation where the camera man or camera woman in this case is moving around with probably the mobile phone camera and filming the situation. And you see that this is quite easy to detect in each frame, but you see at the end, at this current frame T, that we have here a combination of two problems here. So one problem is here that we have an overlapping image of this mirrored cat in this glass, and also we have somewhat a blurred squirrel. And this video object detector makes use of these previous reference frames at t-e, t-e+1, and t-e+2 to then make a good detection for the current frame. So a single frame detector might have problems to detect here anything. And their detector really makes it in a way possible to detect here a cat and the squirrel. Okay, how does it actually work? To go through this quite large architecture diagram, we have to split it into different components. So the first component is that each frame gets through goes through the same blocks. Starting with that, we have one image here. this goes through this CNN backbone. So we have something like that we want to get some features or a feature map for this image. So the input at the beginning is a image of channel 3 because of RGB. We have the width star of the, also star for the original image, and height star. And after that we have, after having a ResNet, for example, we have here a feature map of such a shape of width and height here, where we have C channels, so that could be way more than just 3. Good, so that's here. This feature map, which has like a lot of spatial information from the ResNet, for example, gets then into this spatial transformer encoder. To get a better understanding of this encoder block here, we have to go to this paper, to the end-to-end object detection with transformers paper, which where I will post a link in the description below. So they do here the same, or the current paper is doing the same what they did here in this architecture. So they put it also into a CNN block. They have these image features. They add a positional encoding here so that each feature vector in here knows where in the image it is. These feature vectors are now here. They are then consumed by this transformer encoder and produce feature vectors for each pixel in that feature map here. So these features come out of here. So here we have also these little features here, and they essentially stay here. Then another part is then going one step further to this STD for spatial transformer decoder. So the decoder, we also have to go back to this original paper. So we have now these feature vectors here, and we have here some learned object queries. And these object queries are querying the features from this value and keys from the left side, such that we get feature vectors out of that, which in this paper directly can be put into a feed-forward network to then create bounding boxes and their class. Okay, so having this in mind, we go back here. So we have here these feature vectors from the encoder. They go in. We have these learned object queries. They go then into that STD, so spatial transformer decoder, and create these object proposal feature vectors. And they are then there and can be consumed in the later step. So, and this is now happening for all these different frames in parallel, having different proposals, or they call it now queries because they're going to be used as queries. Okay, so we go now down, And the same thing is done with the current frame. So we go through the CNN, the encoder part, and the decoder part. But the encoded feature map, so we have here again this height and width feature map with C channels, like that, is then put into this block here. Okay, for what stands this TDTE? It stands for Temporal Deformable Transformer Encoder. So why temporal? Temporal because we're gonna have also as input features from different time steps into this attention encoder. Why deformable? Because if we did attention across all these feature pixel here to all other feature pixels in the other images, then we had like a large attention matrices, and these consume a lot of memory. That's why we do something like we choose less key points where we want to attend to. And we go into this deeper just in a minute. And all these features from different time steps are now encoded into a common feature map at the end here. So that it contains like hints and cues of location of possible objects for these images and the current frame. Okay, what means here now temporal deformable attention in detail? So temporal means here in that case that we somehow consume multiple frames at the same time. But first of all, I would like to go into this deformable idea behind that. For that, we have to go to another paper which basically presented this idea of deformability for transformers. Therefore, we go to this paper. It's the paper called Deformable DETR, Deformable Transformers for End-to-End Object Detection. Now we just jump directly to these figures. Let's have a look into the upper one. Yeah, let's take that one. So the idea behind that is, we just imagine we had here these two frames. So we have here our frame at time step t minus 1, and here, so like t minus 1, and here we have the image at a time step, the current one, so like at time step t minus 0. And we have here in this feature map, so we have here again this feature map which looks like that. We have here width and height, and here the channel width, and we have like one feature map here, that tool here. So we have here this feature, and the idea about deformable convolution is that if we have this feature vector here, we want to attend to the other features in this feature map. And the normal attention in these transformers are that there will be like attention across all these pixels. But this is just way too much and way too memory consuming. So the idea then is to make use of this deformable attention. That means we have a fixed number of key points in the feature map where we would like to attend to. So that means we have here our position of our feature. So we get now the position of that feature, but we look at that position in our past image and look with the learned pattern at which feature vector we would like to attend to. So that means that these vectors are learned. Okay, but now one step after the other. So we have here our feature vector from our original or current frame. So it's here in the middle. And that feature vector gets into a linear layer and produces or regresses these offset vectors like that. And these offset vectors are pointing from the same position Q, but in the frame t-1. They are pointing to those features which we would like to use or attend to. So they are pointing to these feature vectors and are then used here and stacked together. Then we have another linear layer with the softmax to normalize these things to 0. That we have like how much attention do we want to have for each of these feature vectors. They get then multiplied and we create here the output for that head number 1. We do this now for multiple heads, so each head can attend to different regions around this fixed point, this point Q here. So for example, head 1 looks more above that feature vector looks maybe more to the side, or any arbitrary thing what the detector can learn. So these different feature vector or attended feature vector, so we got them from attention, they are now then put into another linear layer and are then used as the output for this deformable attention module. So that means our current image chooses on its own what it would like to attend to in the previous frame, for example t-1, or even we can apply this also to other frames like t-2 and 3 and 4 and so on. Okay. Having that said, we go back to this architecture diagram. So we were here that we looked into this TDTE, which stands for Temporal Deformable Attention Encoder. So the question is now again, why have we done this, or why do we have this module? So we have our current frame where we get out a feature map from this encoder. We apply self-attention and then we apply attention across these feature maps from all these different features from all the other frames. And we do it like in a deformable way. Maybe the reason why we do this deformable way is that if we did not do it in a deformable way, then we would attend to all other pixels in the feature map. And this is very memory consuming. And also the deformable attention shows that it learns faster. So that means we have now here this block like self-attention, temporal, deformable attention, and feed forward. And we can stack this block multiple times. And the output of this thing is then a feature-rich feature map of our image, which also contains temporal information across all the other frames here. Now we look into the TQE, which stands for Temporal Query Encoder. Okay, We look now into the TQE, which stands for Temporal Query Encoder. And as input, it gets these spatial object queries from the current frame, and it consumes all the other object queries from all the other frames from t minus I and t minus I and so on. And the goal of this module, of this temporal query encoder, is to create richer object queries consuming queries from other time steps. Okay, and how do we now get even richer object queries? So the idea is to, first of all, apply cross-attention between the queries of the current frame and the queries of the other frames. That means we can apply, just say, okay, hey, where do I need more attention, and so on. But they do not apply it across all, or you not necessarily have to apply this to all queries at the same time, but they introduce something like a scoring selection mechanism. So they start at the first step with higher queries which are more confident. So they put here a dense layer to get out the probability, and those with a higher probability, they are consumed in the first step, then in the second step, which have less probability, and so on. And they can stack this multiple times. And the output is then, as already said, a richer object query which consumes like temporal information from all the other queries from other time steps. Okay, these feature-richer temporal object queries are then consumed by this module called Temporal Deformable Transformer Decoder. As input, it gets these queries and also these encoded feature vectors we got from the last frames. And these queries, they attend in a deformable way across the feature vectors and produce an output, that's why it's called decoder, such that we have feature vectors which we can then use for the box regression and the classification. Okay, we look now again into depth what this deformable attention actually does here. If we have like 100 temporal object queries and the feature map here. Therefore, we go back to this page here. So what we have is something like that, that we have like 100 of these vectors here, feature vectors, and a feature map here. So that's our feature map with information across all frames. Since we have like 100 of these feature queries, there's no like reference point from one feature map to another. Therefore, they have to put this query feature, which is not directly drawn here, they have to put it through a dense layer to create or to regress a reference point. So we take one of these query features here, so we take one of them, put them into a reference, into a dense layer, and we get our reference point. And around that reference point, we do then this deformable attention, which we have seen before. And then we get back out again a feature vector. And this happens like by the amount of these temporal object queries here. And for each of them, We again also put them into this feed-forward layer, and after that we apply again these feed-forward layers to then create bounding boxes and classes. Okay, now we look into depth into this deformable attention again, where we take like 100 or maybe more or less temporal object queries, and these queries attend to then these feature maps which we have here, which have information from all these frames on the left side. So we have here like one feature map. So in the past we talked about, okay, how do we do attention across two feature maps, like deformable attention in the encoding block, where we have like one feature here and we would like to know the other way around. So we know this is the t-0, so the current frame, and we would like to have features around that reference point with a certain attention pattern here. So this is what we see here on that part here. But now in the decoder block, we have not a fixed frame. So we do not have like two feature maps where we do want to have attention or deformable attention. But here we have these feature vectors like 1, 2, 3, 4, 5, 100 of them. And for each of them, they do not directly have a reference point in one of the, in that feature map they attend to. So what they have to do, and which is not drawn here in this figure, is that they need to apply a function, a dense layer, where they regress the reference point. So that means they take one of these feature vectors, put it into a dense layer, create this reference point, and then they know where they are located. And around that point, they have these sampled offsets and do then this deformable attention. So for each of these queries, they get then a reference point, and around the reference point, they do deformable attention, and at the end, they get a feature vector. Okay, so having said that, we get then here 100 of these feature queries out, and for them we create bounding boxes and classes and get then the results we see here. Okay, to summarize the architecture once again, we have here these frames in the past, 1, 2, 3, 4, 5 frames in the past, and the current frame for which we would like to have objects detected. We let them all run through a CNN backbone, something like a ResNet, which also reduces resolution. Then we apply a spatial transformer encoder in a deformable way. We do this for each of these frames. We do it also for the current frame. This current frame acts as a query and tries to attend through time across these different frames to get its feature what it needs. This module can then be also applied multiple times if needed. And then we have here as an output a feature map, which is quite rich because it contains information from the current frame and the past frame. After the encoder for each of these frames, we also apply a decoder block to get like object queries or object proposals, but they are used like queries. These queries are then ranked and scored, and there's a certain cross attention between the current frame and the past frames across these queries, such that we at the end we get a temporal object query for something like a few hundred of objects we would like to query, and these queries are then applied on top of that feature-rich feature map, such that we get 100 bounding box proposals or classes for this current frame. The way they train this is strongly based on the original paper of end-to-end object detection with transformers, so there's nothing new to that. We directly jump to some nice examples where this architecture can shine. Okay, so they compare here single frames detector, so single frame detector versus the video detector. And as we can see here in the first two rows, which can be compared, so we always compare the top with the lower one, that this strange angle of the camera that we have problems with a single detector, that this detects is as a motorcycle, but the video object detector can detect it as a turtle. Here we see that it's a bird, here a turtle. Here we see that it thinks it's a lizard, but our transvot still thinks it's a turtle. Here we have that it's a turtle, but with a lower confidence, turtle with a higher confidence. Here both are okay. And here again, it thinks it's a lizard, but here with very high confidence, it's a turtle. Okay, I mean, we definitely see that over time we have there a more consistent kind of classification for that object. Here for the zebra, where we have like motion blur effects, the single base frame in the first column, they are more or less the same here, but the zebra in the video object detection in the second one has like the full framing of the zebra, while the first one only has its back. Even for higher motion blur, the zebra confidence is quite high, while in the single frame obviously it stays low. And even if the motion blur is even heavier, then we can here detect this as a zebra. And also here when it almost it's completely out and not clearly visible, the zebra is detected. The last example handles or shows more like benefits in cases of occlusion. So we have here in the rear, we have here this bus, which is not detected, but for the transvot, it kind of have a result for that. In the second frame, it detects here a bus, but the bounding box is at a wrong position, while in the transvot it's working. Here, where the bus is halfly perceivable, we have good results for the transvot. The same holds here for that frame. Here the whole image on both is like, so here it thinks it's a bus, okay, that's right, and here it thinks it's a train. And here at the end again, it detects it as a bus with higher confidence. And also the car in here. This table, which we see here now, is quite also helpful because they turn on or turn off certain components, and they can directly tell, okay, this module has a beneficial effect or not. So at the end, we see that the combination of all components which are novel lead to the best result here. So then we have here another nice visualization where they show the attention of different encoders. So in blue, we see attention of the spatial encoders, while the red ones are these of the temporal ones. And we see that the spatial ones are in blue are more diffuse, while the red are more focused. And if we go back to the architecture, this totally makes sense. So we can essentially get the blue circles we have seen in the picture below when we take these query objects from here and we look through the attention mechanism at which pixels this one is looking at. And we see that it is more diffused. While if we're gonna use these ones here, these temporal object queries, which are in red down below, that they are then more confined here and therefore can have a more closer attention to the object than the diffused one. So if you go back again, we see that, for example, we have here different objects. So let me just zoom in once more. So this rider and this horse, the red ones are more focused on top of it. And this is the case for all of these object detections. So we can say blue is like the single detection kind of, and the red one is the temporal one. So it really can focus more because it has more information over time. Maybe one of the most important things in the eye catcher is that they definitely improve and have their new state-of-the-art detector on a video object detection dataset, so ImageNet VID dataset, and they really could boost it up to 3 to 4 mean average precision points, which is really a lot, comparing that this is an end-to-end learnable system and that it directly works out of the box without having special features or handcrafted features. Okay, that's it. I hope you liked the video. Maybe there will be another video soon. Stay tuned, stay healthy. See you later. Bye.